Okay, for this problem we have a recursively defined sequence. If n equals 0, it's 0. If n equals 1, it's 4. And if anything else other than the first two terms, we define it in terms of things that are 2 back in the sequence. So let's figure out the first few terms in the sequence. Clearly a sub 0 is 0 and a sub 1 is 1. A sub 2 is equal to 2 times the previous term. Or sorry, a sub 1 is 4, I'm sorry. 2 is equal 2 times the previous term minus the term that's 2 back in the sequence plus 8. And so that's 8 minus 0 plus 8 is 16. A sub 3, that's equal to 2 times the previous term minus the term that's 2 back plus 8. So that's 32 minus 4 plus 8 makes 36. A sub 4 is going to be 2 times the previous term minus the thing that's 2 back plus 8. So 72 minus 16 is 56 plus 8 is 64. Now you probably noticed that these are perfect squares. In fact, this one is equal to 4 times 1. This is equal to 4 times 4. That's equal to 4 times 9. That's equal to 4 times 16. And so it looks like we have a pattern that a sub n is equal to 4 times n squared. Now, if you didn't notice that you could factor the 4 out, here's another way to go try to find that. We can see 4 is equal to 2 squared, 16 is equal to 4 squared, 36 is equal to 6 squared, 64 is equal to 8 squared, and so this is equal to 2 times 1 squared. That's 2 times 2 squared. That's 2 times 3 squared, and that's 2 times 4 squared. And so it looks like the pattern is 2 times n squared, which again is going to be 4 times n squared. So it looks like that's the pattern. Okay, so now let's prove this using mathematical induction. So theorem, a sub n is equal to 4n squared. Proof, induction on n. Now, the base case is, this time, we have two base cases, n equals 0 and n equals 1. So the recursive formula requires terms that are the previous term and also the term that's 2 back. So that means when I prove this by induction, I actually have two base cases to worry about, n equals 0 and n equals 1. Now n equals 0, a sub 0 is equal to 0, which is 4 times 0 squared. A sub 1 is equal to 4, which is 4 times 1 squared. So both of these are true. So the two base cases work out. For my induction hypothesis, I actually have two things that need to be assumed. So assume that a sub k minus 1 is equal to 4 times k minus 1 squared, and that a sub k is equal to 4 times k squared. So for this one, we have two things that have to be assumed as opposed to just one. So this is a somewhat different kind of induction problem from most of the ones that we've seen in the past. Before, I'd only have one base case and I have one assumption to make. Here I have to make two assumptions and I have two base cases. And I have to make two assumptions because I have to be able to plug into both of these things when I get to the n equals k plus 1 step. So at n equals k plus 1, a sub k plus 1. Using my definition, that's going to be 2 times the previous term minus the term that's 2 back plus 8. My target that I want to show this is equal to, I want to show that this is equal to 4 times k plus 1 squared. That's my target. And if I can do that, I'm done. Now, I use both of these induction hypotheses. So 2 times 4k squared minus 4 times k minus 1 squared plus 8, and that's true by induction hypothesis. Okay, now it's just algebra to convert this into the target. So that'll be 8k squared. What's here is going to be minus 4 times k squared minus 2k plus 1 plus 8. And so that's equal to 8k squared minus 4k squared plus 8k minus 4 plus 8, which is going to be 4k squared plus 8k plus 4. Then I can factor the 4 out. K squared plus 2k plus 1, which is my target, 4 times k squared plus 1. And so that is the end of the proof that a sub n is indeed equal to 4n squared. I want to mention in passing that it is possible to use the concepts from linear recurrence relations to get this. This is a linear recurrence relation, a second order linear recurrence relation with constant coefficients. It's non-homogeneous. And so it's possible to use techniques from that to get this one without using mathematical induction. However, the characteristic equation has a double root, and we did not consider those kinds of things in class, not because it's particularly hard, but I just didn't want to spend time on that in class. So the techniques that I used in class will not get this one, but it is possible to use linear recurrence relations in order to solve this problem, even though I'm not doing it on this video.